In the last set of videos, we explored rotational kinematics. We saw that there was some parallel between rotational kinematics and one-dimensional translational kinematics. And we'd like to continue to explore that parallel. So we found in one-dimensional translational kinematics that a force was what was causing an acceleration and ultimately a change in velocity. Now we'd like to talk about what causes a change in angular velocity and ultimately the angular acceleration. And this is introducing a concept called torque. So torque is going to be defined as the cross product between a distance vector and the force. So if you have some force acting at some distance, this is going to give you the torque. Another way that this can be defined is to say that the torque is going to be this distance times the force times the sine of the angle between them. Now, so far this is kind of mathematical, but let's actually explore this in more of a physical context. And that's to explore how this looks with this wrench. So R, the distance, is going to be the distance from the point of rotation for this wrench to the position where we're acting this force. And now, when we think about torque, it's important to realize that in order to maximize the torque here, we would want to act this force as far away from the pivot point as possible. But we'd also want this force to act perpendicular to this distance vector. So if we had this force acting in the same direction as the distance vector, we're not going to cause any rotation at all. In order to cause rotation, this force needs to be perpendicular to this distance vector. When we talk about torque, another area that we can explore is what's called static equilibrium. We've actually already been discussing some cases of static equilibrium, but these were somewhat simplified cases where there were no possibilities of rotation. So in general, when we talk about an object being in static equilibrium, we say that the sum of the forces is equal to 0. And what this means is that if the sum of the forces is equal to 0, the object can't accelerate in any direction. It's going to be fixed in position. Now, an additional condition for static equilibrium is that the sum of the torques is equal to 0. And what this says is not only does the object not translate, doesn't move up or down or left or right, it also doesn't rotate. And so for something to truly be in static equilibrium, it both needs to have a sum of forces equal to 0 and a sum of torques equal to 0. Now the case of static equilibrium is a special case. This is a case when we said that both the angular acceleration and the translational acceleration are 0. But we saw previously when we were looking at Newton's second law that forces don't always sum to 0. They can sum to a mass times acceleration. This is the more general case of Newton's second law. We have something very similar for torques. And so that's to say that the sum of the torques is going to be equal to this term I, which is called the moment of inertia, times alpha. So let's discuss in some qualitative ways what the moment of inertia means and do this by comparing it to the mass. So imagine that you apply some force to an object, some fixed force to it. It's going to accelerate. Now, if that object has a larger mass, it's going to accelerate less. And so what you can say is the mass tells you something about how difficult it is to accelerate an object. Now, if we think about the moment of inertia in this way, it makes a lot of sense because what the moment of inertia tells us is how difficult it is to rotate something. So say I have some object and I apply some torque to it about some point. If it has a small moment of inertia, it will rotate very easily. But if it has a large moment of inertia, it's more difficult to cause it to rotate. In this video, we introduced the concept of torque in order to explore the question, how does an object gain some angular acceleration? We saw in doing this that there was some parallel between the torque for rotation and the force for translation. We also saw that this parallel can be taken even further in order to compare the mass to the moment of inertia. In the next videos, we'll be discussing how we can apply these new concepts in order to solve some problems.